In this video, we're going to take a quick look at how you can prove inequalities using the mean value theorem. Well, actually, we're going to use a consequence of the mean value theorem. We're going to prove a couple of inequalities using the increasing-decreasing function theorems. The increasing-decreasing function theorems tell you something about how a function behaves based on the derivative. So, for example, if your derivative is positive on an interval, then that function is increasing on that interval. On the other hand, if your derivative is negative on an interval, then the function is decreasing on that interval. And we're going to make use of these theorems in order to prove a couple of inequalities. The first one we're going to prove is we're going to show that sine of x is less than or equal to x for all x greater than or equal to 0. And we're going to show this by defining a new function that provides a measure of the distance between sine of x and x. So let's start by letting f at x be our function. And it's just going to be the difference between x and sine of x. So this just measures the distance between the two. Now, what we're going to show is that this function is an increasing function. And we can show that just by looking at the derivative. So f prime of x is equal to the derivative of x is 1 minus the derivative of sine is cosine of x. Now cosine of x is bounded above by 1. That means that cosine of x is always less than or equal to 1. So in particular, 1 minus cosine of x is always greater than or equal to 0. In particular, what this means is that f prime of x is never negative. And that means that the function f is never decreasing. And this is the key idea. Why is that the key idea? Well, let's just ask ourselves, what do we know about f? Well, f measures the distance between x and sine of x. And there is a particular point where those two coincide, namely at x equals 0. So at x equals 0, we have that f at 0 is equal to 0 minus sine of 0. But sine of 0 is also 0, so this is just 0. Notice that we're looking at the interval where x is greater than or equal to 0. So you think of 0 as the starting point. We start at x equals 0. And at x equals 0, this function is 0. But the function f is never decreasing. That means this value, 0, is the smallest it can be. So this is the smallest possible value for f at x on the interval where x is greater than or equal to 0. Well, if that's the smallest possible value, then that means that f at x is greater than or equal to 0 for all x greater than or equal to 0 for all x on the interval. But this is really all that we need, because what was f? F at x is x minus sine of x. And now we know that this is greater than or equal to 0 for all x greater than or equal to 0. And if you just add sine of x to both sides, that's going to give us exactly what we want. We're then going to have that x is greater than or equal to sine of x for all x greater than or equal to 0, which is what we wanted to show. Now, if we look at the graph, we can see exactly what's going on here. So we have this graph right here is y equals x. That's the blue dashed line. The solid line is y equals sine of x. The function f at x tells us the error between these two, or the distance between these two. if you pick a specific value of x, like this one, then the output value on the solid curve is sine of x, and the output on the dashed blue curve is x. So the vertical distance between these two is exactly f at x. And you can see that as x moves to the right, we start off at 0. That's the smallest it can be. But as we move further to the right, this distance, this error term, gets larger and larger and larger. And so what we're seeing is that x minus sine of x starts off as 0, but then that distance between the two gets larger and larger and larger. So x minus sine of x gets bigger and bigger and bigger. And that's what we see when we show that the derivative is greater than or equal to 0. That means that the function f is getting larger, or at the very least it's not getting smaller. Now notice that this isn't true if we look at x negative, because we have the reverse relationship if we're looking at when x is negative. Now one thing about this inequality, that x is greater than or equal to sine of x, at a certain point this becomes trivial, because when x is greater than or equal to 1, then automatically x is greater than or equal to sine of x, because sine of x can never be greater than 1. Sine of x is always less than or equal to 1. So once x is at 1, then this inequality just becomes trivial. But between 0 and 1, this is an interesting fact, because it's not immediately obvious that these two curves don't actually intersect at any point other than x equals 0. Let's look at another example. Let's show the inequality e to the x is greater than or equal to 1 plus x for all x. Now we're going to approach this one in the same way, but there's a little thing that we have to be careful about. In the last example, we were just looking at x greater than or equal to 0. Here, we're looking at all x, and that's going to affect how we deal with this. But we're going to start the same way. We're going to define a function, which we might as well call f, and this is just the difference between the two. So it's e to the x minus 1 plus x. Or perhaps the way we want to write this is f at x is equal to e to the x minus 1 minus x. And now what we're going to do is we're going to look at the derivative. F prime at x is equal to, well, the derivative of e to the x is e to the x minus the derivative of 1 is 0, but then the derivative of x is 1. So it's going to be e to the x minus 1. Now what's important here is that this is not always positive. Sometimes it's positive, but sometimes it's negative. So note f prime at x is equal to 0 when x is equal to 0. And in fact, what you can show is you can show if you draw a little number line, if this is 0, then when x is negative, you see that f prime of x is less than 0, and when x is greater than 0, then f prime at x is greater than 0. Now, we know that this is true because we have a formula here. Now, when x is actually equal to 0, e to the 0 is 1. But once x is bigger than 0, once x is positive, then this e to the x is going to be bigger than 1. So you'll have a positive value. But if x is negative, then this becomes 1 over e to the something positive. So that means it's less than 1. So you end up with a negative value. So what does the derivative being negative tell you? Well, if the derivative is negative on an interval, that tells you that the function is decreasing there. And similarly, if you're on an interval where your derivative is positive, that means the function is increasing. So as long as x is greater than 0, then f prime of x is positive, so f is increasing there. So our error term is decreasing in size when x is negative, but our error term is increasing in size when x is positive. Now we can see this if we look at the graph. And you can see that the vertical distance between these two graphs, if we look at an x which is negative over here, you can see that we have a vertical distance giving us the error. And so this is our f at x here. And as x moves to the right, this vertical distance is getting smaller and smaller. So the error is decreasing. But then once you get past the y-axis and your x's are positive, your error term gets larger and larger and larger. So as x moves to the right, your error term, which is just this f at x, gets larger and larger and larger. So you can see that at first the error term is getting smaller, and then the error term is getting larger. Well, notice that there's one spot where they actually agree, and that's at x equals 0. So let's just go back to looking at our function. And our function is, of course, f at x equals e to the x minus 1 minus x. And what did we establish? We established that when x is negative, this error term is decreasing. And when x is positive, our error term, is increasing. So we have this dichotomy here. When x is negative, f is decreasing, but when x is positive, f is increasing. What we also know is that f at 0 is equal to e to the 0 minus 1 minus 0, but e to the 0 is 1, so this is just 0. So let's look at the case when x is negative. So when x is negative, this function is decreasing. This error is decreasing. So the smallest that it can be is at the end of the interval. So when x is negative, we're looking at the interval. The interval in question is the interval from minus infinity to 0. And it's decreasing on this interval. So that means the smallest it could possibly be is when x gets to 0. So f at x is smallest at x equals 0. So what that tells us is that f at x is greater than or equal to 0. But of course, f at x is e to the x minus 1 minus x greater than or equal to 0. So if you add 1 and x to both sides, you'll have e to the x is greater than or equal to 1 plus x. And that's exactly the inequality we wanted to show, but we've only shown it for x less than 0. So this is the case where x is less than 0. Well, what about the case when x is greater than 0? What about this case? Well, it's the same idea. Now, in this case, we still start when x equals 0. And that's still going to be e to the 0 minus 1 minus 0 is equal to 0. That hasn't changed because our function f hasn't changed. It's just that now we're looking at a different interval. So when x is greater than 0, our interval is the interval from 0 to infinity. And on this interval, we know that f is increasing. So what does that mean? That means that it's getting bigger and bigger. So the starting point, x equals 0, if the function is increasing, then the starting point is the smallest. Well, that's when x is equal to 0. So f at x is smallest there at x equals 0. So that means that f at x is greater than or equal to its smallest value for all x greater than 0. So what is f at x? It's e to the x minus 1 minus x, and this is greater than or equal to 0 for all x greater than 0. So again, you add 1 and you add x, and you have that e to the x is greater than or equal to 1 plus x for all x greater than 0. And again, we've proved our inequality for x greater than 0. Well, we've shown that it's true when x is less than 0. We've shown that it's true when x is greater than 0. And these two quantities here are equal at x equals 0. They're both 1. So that tells us, putting all this together, so e to the x is greater than or equal to 1 plus x, well, if it's true for x less than 0, and it's true for x greater than 0, and you actually have equality when x is equal to 0, then it's true for all x. Notice that this is an inequality greater than or equal to, so that means we're allowing for equality. So now we've shown that this inequality was true for all x, and that's what we wanted to show.